Namaste everyone and welcome to day 8 of our 15-day beginner data science sprint. In the previous lesson, we learned how to visualize data using Matplotlib and Seaborn. We created bar charts, line charts, histograms, box plots, and scatter plots. But creating individual charts is not the same as conducting an analysis. Today we are going to combine statistics, grouping, and visualization to perform something called Exploratory Data Analysis or EDA. The main question for today is, before building a machine learning model, what story is the data already telling us? By the end of this lesson, you will be able to perform univariate, bivariate, and group analysis, identify patterns and possible outliers, spot potential data quality issues, create and interpret a correlation matrix, and separate an observation from an explanation. Most importantly, you will learn how to avoid one of the biggest mistakes in data analysis, that is, treating every relationship as proof of causation. Let us begin. What is data analysis? Exploratory data analysis is the process of systematically investigating a dataset before building a model or making a final conclusion. Notice that I used the word systematically. EDA is not about creating random charts until something interesting appears. A good EDA process follows a structure. So, what is EDA? I am writing it down. So, we normally begin by asking these questions. So, what variables are available? That is the first question. What does each variable represent? Second question. How is each variable distributed? Are there any missing, unusual, or impossible values? Which variables appear to move together? How do different groups compare? What can we observe? What what can we not conclude from the data? All these questions we ask in the beginning. EDA helps us to understand whether a dataset is suitable for answering our question. It can also reveal problems that should be corrected before modeling. For example, imagine that a student has an attendance value of 250%. A chart may display that value, but the chart does not automatically tell us that the value is incorrect. We must investigate it. Similarly, suppose students with high attendance tend to have high final scores. That is an observation, but it does not automatically prove that attendance alone caused the higher scores. Those students may also study more, participate more, or have stronger previous academic performance. This difference between association and causation is extremely important. Let us begin by importing the libraries required for today's analysis. Pandas will help us inspect group and summarize the data. So Pandas will help us inspect group and summarize the data. Matplotlib and Seaborn will help us create visualizations. Now let us load the clean student performance dataset that we prepared in the previous lesson. So we need to write this code. Let me rename it. And let us run again. Now let us display the first 5 rows. So we are seeing the first 5 student records and the columns available in the dataset. We can now see fields such as student ID, study hours, attendance, previous score, sleep hours, participation level, and final score. Your exact dataset may contain some additional columns, but the investigation process will remain the same. Before analyzing anything, let us create a simple checklist. I usually divide EDA into 4 stages. So EDA checklist equals the first stage is understanding the dataset structure. The second stage is analyze individual variables. Third is to analyze relationship between variables. Then fourth is to compare meaningful groups. Then I print the steps. Run the cell. Our EDA process will therefore be first understand the dataset, second inspect individual variables, third study relationships, fourth compare subgroups. This sequence prevents us from jumping directly to conclusions. Let us begin by checking the size of the dataset. The first number represents the number of rows. The second number represents the number of columns. Now let us examine the column names. Next, we will inspect the data types and missing values. So we know now which columns are numerical, which columns contain text or categories, whether any column contains missing values, and whether the number of non-null values is consistent. Remember that df.info is not an analysis by itself. It is an initial diagnostic check. It tells us how the dataset is organized. It does not tell us whether every value is logically correct. For example, attendance may be stored as a numerical value, but we must still check whether it falls within a sensible range. Let us also check for missing values. Because we cleaned the data in day 6, we expect very few or no missing values and duplicate rows. However, it is still good practice to confirm this. Never assume that a dataset is clean merely because its file name contains the word cleaned. For today's numerical analysis, we will focus on these columns. Let us generate summary statistics. So describe calculates the number of available values, the mean, the standard deviation, the minimum, the first quartile, the median, the third quartile, and the maximum. Take a moment to inspect the output. Do not try to inspect every number immediately. Start with a few simple questions. Are the minimum and maximum values realistic? Is the mean very different from the median? Is one variable much more spread out than another? Are there possible extreme values? So after looking at this output, we should ask these questions. For attendance, we would normally expect values between 0 and 100. For final scores, we may also expect values between 0 and 100. If we see a negative score or attendance above 100, that may indicate a data quality issue. For study hours and sleep hours, we should also check whether the maximum values are believable. A value may be statistically unusual without being incorrect. That is why EDA identifies values for investigation rather than automatically deleting them. Univariate analysis means analyzing one variable at a time. The purpose is to understand the distribution, typical value, spread, and unusual observations of a single column. Let us begin with the final score. Before running this cell, predict what you expect to see. Do you think most students will be concentrated around the middle? Will the scores be evenly distributed? Will there be a few very low or very high scores? Run the cell. The histogram groups scores into intervals. The height of each bar represents the number of students within that interval. The smooth line gives us another view of the overall shape of the distribution. From this chart, we may observe that most scores are concentrated within a particular range. We may also notice a few students with unusually low or high scores. However, this chart does not explain why those students received those scores. It only shows the distribution. That distinction is important. And observation could be most final scores are concentrated between approximately 60 and 85. So after looking at this graph, this is one of the observation. And this is one of the unsupported explanation. So this thing is wrong, this thing is correct. So let me write it as wrong. The dataset does not contain enough evidence to prove that the examination was easy. Always separate what you see from why you think it happened. Let us inspect attendance. Before running the cell, think about what a reasonable attendance distribution might look like. We can now see whether attendance is concentrated at the higher end, spread evenly, or divided into multiple groups. Again, we should describe the visible pattern before attempting to explain it. For example, most students have attendance above 70%. This is an observation. And if someone is saying that students attended regularly because they enjoyed the course. That is an unsupported explanation. There is no evidence of this fact in the data set. That is an explanation which the dataset does not prove. A a histogram helps us understand the overall distribution, but a plot is particularly useful for identifying possible outliers. Let us create a box plot for the final score. Run the cell. The box represents the middle 50% of the data. The line inside the box represents the median. The whiskers extend towards the more typical lower and upper values. Points beyond the whiskers may be possible outliers. The word possible is important. A value shown outside the whiskers is not automatically an error. It may represent a genuine student who performed very differently from the rest of the class. We should inspect such records before making a decision. Let us calculate the interquartile range. So the formula to calculate the code to calculate that is on that column we write dot quantile, either it can be 0.25 or 0.75, and then we find IQR by Q3 minus Q1. Now let us display the records outside these boundaries. I want to tell you that we should give more focus on the process of exploring the data rather than the code, because the code can simply be generated. I could ask from the Gemini that to generate the code to get the IQR, and then give me the scores which lie outside the IQR. Give me those rows. So that can be generated. But the thing that we need to generate this, that is required to be known by you. So we are getting the complete rows for students whose final scores fall outside the calculated range. Now we can investigate these students. We can compare their study hours, attendance, previous scores, sleep hours, participation levels, and final scores. An outlier may be an array. It may also be an important real world observation. For example, a student may have studied for many hours but still received a low final score. That student could help us discover that study time alone does not explain performance. Bivariate analysis means examining the relationship between two variables. Let us investigate whether study hours and final scores appear to be related. Before running this cell, make a prediction. If study hours are positively associated with the final scores, what should the points look like? You may expect the points to generally move from the lower left towards the upper right. Run the cell. Look at the overall direction rather than focusing on a single point. If students who study more generally have higher scores, we can describe this as a positive association. But we should not say studying more always causes a higher score. Why not? Because there may be students who studied for several hours but still scored poorly. There may also be students who studied less but had a strong previous knowledge. The scatter plot only shows how two recorded variables move together. It does not control for every other possible factor. A defensible observation would be students with more study hours generally appear to have higher final scores, although there are exceptions. This sentence describes both the broad pattern and its limitation. This sentence describes both the broad pattern and its limitations. Now let us compare attendance and final score. Before running the cell, predict the direction of the relationship. Run the cell. Suppose the points show that the students with higher attendance generally have higher final scores. We may write higher attendance is associated with higher final scores in the dataset. Notice the wording. We said associated with, not caused. We have not conducted a controlled experiment. Other factors may influence both attendance and performance. We can add a regression line to make the overall direction easier to see. Run the cell. This line summarizes the general linear trend. If the line slopes upward, the two variables have a positive relationship. If it slopes downward, they have a negative relationship. If it is almost flat, there may be a little linear relationship. But remember, a trend line is a summary. It does not mean every student follows the trend. It also does not prove that changing one variable will directly change the other. Sometimes a continuous numerical variable is easier to interpret when divided into meaningful groups. Let us divide attendance into three bands: low, medium, and high. Let us check new column. Run the cell. Each attendance percentage has now been placed into a category. Students with attendance up to 70% are in the low group. Students with above 70 and up to 85% are in the medium group. Students above 85% are in the high group. These boundaries are analytical choices. They are not universal laws. A different school or institution may define attendance bands differently. Whenever you create groups, document how the groups were defined. Let us compare final scores across attendance bands. Before running the cell, predict the output. For each attendance group, we expect to see the number of students, the average final score, the median, the minimum, and the maximum. Run the cell. Suppose the high attendance group has a higher average and median final score than the low attendance group. We can say students, so one valid observation can be students in the high attendance group had higher average and median final scores than students in the low attendance group. This is a valid observation, but we should not immediately say high attendance caused students to score better. Students with high attendance may also differ in study habits, previous scores, participation, or other factors. Let us visualize the comparison. Run the cell. The box plot allows us to compare the median score, the spread of scores, overlap between scores, and possible outliers. Even when one group has a higher median, the groups may still overlap substantially. That overlap is important. It reminds us that attendance is not the only factor connected with performance. So you don't need to memorize the code. How exactly? Because we can generate the code. What we want, that should be clear. We want final scores by attendance band. The box plot of the final scores by attendance band. So we can write and generate the same code. For example, I can do that. I want to see the box plot of final score with attendance band. And I'm using the model Gemini 2.5 Flash, which is the cheapest model. So it is saying that it has already been generated and is available in the cell this. So let me delete this and let me ask to do it again. So I will create a new chat, copy that, create new chat, paste it, enter. So as you can see, I've got it and I will accept it. Let's move it down and let us now run it. So I'm getting the correct result. So what I need to know is what I want, and that thing, that code will be generated. Even when a group has a higher median, the groups may still overlap substantially. That overlap is important. It reminds us that attendance is not the only factor connected with performance. Now let us compare scores by participation level. First, inspect the available categories. Run the cell. We may have categories such as low, medium, high. Now let us calculate group statistics. Before running the cell, predict which participation group may have the highest average score. Run the cell. We can now compare the number of students and the typical score within each participation group. The count column is important. Imagine that the high participation group has an average score of 92 but contains only 2 students. That average would be less stable than an average calculated from 100 students. Always consider group size when interpreting averages. Let us create a bar chart. Run the cell. A possible observation could be average final scores increase across the low, medium, and high participation groups. A possible limitation could be the groups may differ in study hours, attendance, or previous academic performance. That is the style of interpretation we want to develop. So after looking at this bar chart, we can have this observation. Average final scores increase across the low, medium, and high participation groups. And a possible limitation would be this. The groups may differ in study hours, attendance, or previous academic performance. We can also compare attendance bands and participation levels together. Before running the cell, predict the output. The rows will represent attendance bands. The columns will represent participation levels. The values will represent average final scores. Run the cell. This table helps us ask more focused questions. For example, do highly participative students perform well even with medium attendance? So let us see the table once again. df dot height. So these are the questions that we can ask now. Do highly participative students perform? So these are the questions after looking at above table. Do highly participative students perform well even with medium attendance? Do low participation students perform differently across attendance bands? Are some combinations represented by very few students? We must be careful with empty or very small groups. A missing value in this table may simply mean that no student belongs to that combination. It does not necessarily indicate a data error. Let us visualize the table as a heat map. Run the cell. Darker and lighter cells help us quickly identify which combinations have higher or lower average scores. However, the heat map can hide group sizes. A high average based on two students may appear visually important. Therefore, we should always compare this chart with the number of records in each group. This is a good example of why EDA requires multiple outputs. One chart rarely tells the complete story. Now let us calculate correlation between the numerical variables. Before running the cell, predict what the output will look like. It will be a square table. The same variables will appear in both the rows and columns. Each value will normally fall between -1 and +1. Run the cell. A correlation close to +1 indicates a strong positive linear association. A correlation close to -1 indicates a strong negative linear association. A correlation close to 0 indicates a weak linear association. Every variable has a correlation of 1 with itself. That is why the diagonal contains ones. Let us visualize this matrix. Run the cell. The annotation display the numerical correlation values. The colors make stronger positive and negative association easier to identify. Look at the row or column for final score. Which variable has the strongest positive correlation with it? So it may be study hours, previous score, attendance, or another variable. Your result will depend on the dataset. Suppose previous score has the strongest correlation with the final score. A defensible observation could be So this could be observation. Previous score has the strongest positive linear association with final score among the variables examined. What does this not prove? It does not prove that previous score directly causes the final score. Previous score may represent earlier knowledge, consistent effort, or other characteristics that are not separately recorded. Also remember that correlation mainly measures linear relationships. Two variables may have a meaningful curved relationship but still show a weak linear correlation. Correlation is useful, but it is not a complete explanation. Let us compare the average values across attendance bands. Run the cell. This table allows us to inspect whether the attendance groups also differ in other ways. For example, high attendance students may also have higher study hours, higher previous scores, or different sleep patterns. This is important because it reveals possible confounding factors. A confounding factor is another variable that will be related to both the factors we are studying and the outcome. For example, suppose attendance and final score are positively associated, but high attendance students are also study more. In that case, study hours may partly explain the observed difference in final scores. EDA helps us discover these possibilities. It does not always resolve them. Averages describe broad patterns, but unusual cases can be equally informative. Let us find students with high attendance but relatively low final scores. So we are looking for students who attended regularly but still received a low final score. If such records exist, they remind us that attendance alone cannot fully explain performance. Now let us find students with lower attendance but high final scores. These exceptions are not inconvenient data points that should be ignored. They help us understand the limitations of simple conclusions. A broad trend can be real even when exceptions exist. Good analysis describes both. Let us pause and clearly distinguish between an observation and an explanation. An observation describes what the dataset shows. For example, students in the high attendance band have a higher median final score. An explanation proposes a reason. For example, students in the high attendance band scored better because they listened carefully in every class. The first statement is supported by the data. The second statement may be possible, but it is not directly proven by the available columns. A better analytical statement would be students in the high attendance band have a higher median final score, although this difference may also be connected with study hours, previous scores, or participations. This statement contains the observation, uncertainty, and an alternative explanation that makes it more defensible. So, after looking at these data, we can come up with this statement. Let us pause for today's checkpoint. Look at the correlation matrix, the group attendance analysis, or the participation comparison. Choose the output that you think is most important. Now explain it in one sentence without using technical jargon. Pause the video and write your sentence. Do not use words such as correlation coefficient, distribution, statistical significance, or regression. Explain the result as though you are speaking to someone who has never studied data science. For example, students who have attended more classes generally received higher final scores, but attendance was not the only factor connected with performance. This is much clearer than saying attendance has a positive correlation with final score. Technical language can be useful, but only when we also understand the real meaning. Now it is time for your day 8 challenge. Your task is to write 3 observations from the dataset. For each observation, also write one alternative explanation or limitation. So this is your learner challenge. Write 3 observations from the dataset. For each observation, also write one alternative explanation or limitation. Use this format. So you may use a distribution, a scatter plot, a grouped summary, a box plot, or the correlation matrix. Here is one example. So the example is this. Observation could be students in the high attendance group have a higher average final score. Evidence is the group summary shows a higher mean score for the high attendance band. Alternative explanation and limitation is high attendance students may also study more or have stronger previous scores. So this is one example observation. Now pause the video and write your 3 observations. Let us discuss one possible approach. Start with the attendance band summary. The input is the student dataset. The operation is grouping students by attendance band and summarizing their final scores. The output is a table containing the number of students, average score, and median score for each group. From this output, your first observation will compare the low and high attendance groups. Next, you can use the scatter plot between study hours and final scores. Your observation may describe the overall direction. Your limitation may mention exceptions or other unmeasured factors. Finally, you can use the correlation matrix. This gives us a focused view of how each numerical variable is associated with the final score. Do not copy my observation word for word. Use your own output and explain what you actually see. The most important mistake to avoid today is calling every visible relationship as a cause. Suppose we observe that students who sleep more tend to have higher scores. Can we conclude that additional sleep directly cause the higher scores? Not necessarily. Students with healthy sleep patterns may also follow better routines, study more consistently, experience less stress, or have other advantages not recorded in the dataset. Similarly, suppose high participation is associated with better scores. Participation may help learning, but students who already understand the subject may also feel more confident participating. The direction of the relationship is not always clear. Observational data usually supports statements such as is associated with, tends to be higher, appears related, differs across groups, or shows a pattern. It usually does not support statements such as definitely caused, always leads to, guarantees, or proves. Good analysts are careful with language because careful language reflects careful thinking. Careful language reflects careful thinking. We can organize some of today's outputs into a compact report. Run the cell. This gives us a repeatable starting point for future datasets. However, do not treat this code as a universal EDA formula. Every dataset requires questions based on its context. A healthcare dataset, financial dataset, or customer dataset may require completely different checks. The checklist provides a structure. The domain determines the exact question. After completing the analysis, write one final interpretation in a single sentence. For example, final scores are generally higher among students with stronger attendance, participations, and previous scores. Although these relationships do not prove that any single factor directly caused better performance. This sentence summarizes the broad pattern. It also acknowledges the limitation. Your exact interpretation should depend on the output produced by your dataset. Let us recap what we learned on day 8. Exploratory data analysis is a structured investigation of a dataset. We begin by examining the dataset structure, data types, missing values, duplicates, and descriptive statistics. We then performed univariate analysis to understand individual variables. We used histograms and box plots to inspect distributions and possible outliers. Next, we performed bivariate analysis. We used scatter plots to investigate relationships between numerical variables. We created attendance bands and compared final scores across meaningful groups. We analyzed participation levels using counts, means, and medians. We created a correlation matrix to compare linear association between numerical variables. Most importantly, we separated observation from explanation. We learned that correlation suggests association, not causation. So, what new capability did we gain today? We can now turn a broad dataset into focused analytical questions and defensible observations. And which output should you be able to explain without looking at your notes? You should be able to explain one important pattern, the evidence supporting it, and one limitation or alternative explanation. So these are two questions that you need to answer. What new capability did we gain today, and which output should you be able to explain without looking at your notes? In the next lesson, we will move further into the data science workflow and use what we discovered during EDA to prepare the data for machine learning models. Complete the learner challenge. Save your notebook as day 8 exploratory data analysis.ipynb and add one final sentence explaining the most important pattern you discovered. I will see you in day 9.